Hello everyone, welcome to the part 2 of our discussion on soil formation and development. Last time we have finished with the soil forming factors such as the climate, living organisms, relief, parent material, and time. So this time we will relate all those soil forming factors with the soil forming processes. So let's begin. When you say soil formation, it is synonymous to soil genesis. It is the process of creating soil from not soil, and this not soil is the parent material. Soil genesis includes the following: reducing the size of the parent material particles, rearranging the mineral particles, adding organic matter, changing the kinds of minerals, creating horizons, and producing clays. This is a continuous but very slow process, when in fact it will take thousands or billions of years in order to make at least or to develop at least 1 centimeter of soil. There are four soil forming processes, and these are transformations, translocations, additions, and losses. This one is a diagrammatic representation of the four soil-forming processes such as the transformations, translocations, additions, and losses. Now for transformations, transformation is here. It involves weathering of primary minerals to clay and hydrous oxides. It also involves the humidification of organic matter. While translocations involves the transfer or movement of clay, organic matter, salts, and sesqui oxides by water upward, downward, or horizontally or vertically on the soil profile. It also involves transfer or movement of nutrients by plants or movement of soil particles by animals. Additions involve addition of water, oxygen, carbon dioxide, nitrogen, organic matter, sediments, and energy coming from the atmosphere and the sun. While losses includes evapotranspiration, denitrification, radiation of energy, erosion of sediments, and losses of water and minerals through leaching. So this is a very good diagrammatic representation or summary of the four soil forming processes. Let us now have a deeper discussion on the transformation processes. Transformation occur when soil constituents are chemically or physically modified or destroyed and others are synthesized. These include the weathering of primary minerals, the composition of organic residues, synthesis of organic acids, humus, and other products, and change in the size or arrangement of particles. The parent materials are transformed into silicate clays through chemical and physical weathering. And the silicate clays and the composition products recombine to form new minerals such as the hydrous oxides of iron and aluminum, or collectively called sesqui oxides. Organic materials decompose and are incorporated into the mineral aspect of soils, and other organic products, such as organic acids and humus, are synthesized from organic materials. Included in the transformation process is the weathering of large particles that can cause the formation of smaller particles, and these particles can be arranged and built into aggregates, therefore developing the soil structure. Let us define what is weathering. Weathering is any of the chemical or physical processes by which rocks undergo chemical decomposition and physical disintegration. There are two types of weathering, and it usually occurs at the Earth's surface. And the results of weathering could be changes in color, texture, composition, or hardness of the affected rocks. And this process is controlled largely by climate. The more water is available, the more likely the chemical processes can proceed. In arid climates, weathering processes move very slow. Why is that so? It is because of relatively lower rates of rainfall. Physical weathering will be dominant process in these areas, but since it relies on the chemical weathering, it will also be quite slow. The first type or first kind of weathering is the physical weathering. It includes the breakdown of rocks and minerals by physical forces. No? An example is this. No? When the plant aids in the weathering of rocks, as you can see, the rocks or the rock breaks into two. We have different factors and processes associated with physical weathering. The first one is the wetting and drying. In wetting and drying, the soils that are wetted up may be prone to swelling, then shrink when they dry out. These seasonal effects are termed shrinkage and swelling. And subsidence is based upon shrinkage and swelling place under foundation. So this happens when, for example, it rained and the soil is wetted up, it will swell. While during the dry season, because there is no enough water, the soil will shrink. Another process is the freezing and thawing or melting. Water expands considerably when frozen, and this expansion literally pushes the soil apart, therefore breaking it down. When the ice thaws, the soil can slump back again. And this overall process of freezing and thawing is like a very slow churning. And this process can literally grind mountains over time. Another factor or process is the heating and cooling. The extremes of temperature can cause the soil to expand and contract. The effect is less pronounced than that of freezing and thawing, but over time, this can become significant. There is also the process of grinding or rubbing. The grinding of particles against each other leads to particle disintegration. And this one is commonly or most obvious on the beaches wherein the evidence of abrasion by water can be clearly seen. The wind-blown dust and sand can also wear down rocks by abrasion. Another process is the unloading. When pressure is placed upon a soil, for example, a glacier on soil, it becomes compressed. And then when ice melts, a huge weight is lifted and the soils may react accordingly by uplifting and expanding. We also have the organisms. As what I have discussed in the previous video, this can also affect the factors or the processes of soil formation. For plants, there are the plant roots that can pushed through the soil. While for animals, for example, there are worms that can burrow their way through soil, mixing and aerating it all throughout their lives. We are now finished with physical weathering. Now we move on with the chemical weathering. No? So we have physical and then we have chemical weathering. Chemical weathering is in which the rocks are decomposed, dissolved, or loosened by chemical processes to form residual materials. Chemical weathering takes place in almost all types of rocks. Smaller rocks are more susceptible because they have a greater amount of surface area. Now remember in chemistry, the larger or the greater the surface area, the more reactive it would be. And as what I've said earlier, chemical processes or chemical reactions involving chemical weathering is much more common in locations where there is a lot of water. And chemical weathering could be enhanced by geological agents. When you say geological agents, it involves the presence of water and oxygen, as well as biological agents. When you say biological agents, this involves the acids produced by microbial and plant root metabolism. Thus, we have the term biogeochemical weathering. So let me discuss now the different factors or different processes involved in chemical weathering. One is we have dehydration. Hydration is a process where minerals in the rock absorb water and expand, therefore creating stress which causes the disintegration of rocks. And the resulting product of this is softer, more stressed, and more easily decomposed mineral. For example, you have for initially an unhydrated calcium sulfate. When that unhydrated calcium sulfate reacts with water, of course, calcium sulfate will become hydrated and it will expand or it will swell. Another process is hydrolysis. It refers to the chemical reaction between the minerals in the rock and hydrogen in rainwater. When water molecules split hydrogen ions and hydroxyl ions components, the hydrogen ion often replaces a cation from the mineral structure of the rocks. For example, during hydrolysis, the potassium feldspar of the granite changes to clay mineral kaolinite, which crumbles easily, weakening the rock and causing it to break down. We also have what we call carbonation. It is the process by which dissolved carbon dioxide in rainwater or moisture in surrounding air forms carbonic acid and reacts with the minerals in the rock. For example, when rainwater reacts with carbon dioxide, it will form the carbonic acid. And when carbonic acid reacts with limestone, this will form calcium bicarbonate, which is soluble. Chemical weathering also involves dissolution. This is the process by which minerals in the rocks dissolve directly in water. When the rocks dissolve, the materials which make them up become ions in solution in the water and are carried away with it. For example, when gypsum dissolves in water, the ions composing it will dissociate, such as the calcium and the sulfate ions. The last one we have for chemical weathering is the oxidation. Oxidation takes place when oxygen combines with other elements in rocks to form new types of rocks. And these new substances are usually much softer and thus easier for other forces to break apart. Sometimes, a change in the color of a rock means that oxidation process has occurred. One common example is the oxidation process of iron. When is oxidized, it will form the rust or iron oxide, which crumbles easily. So these are examples of rocks that are rusting or have undergone oxidation process. And this one is an example of dissolution, where water has dissolved the limestone that once occupying the voids. So we are now finished with the transformations. We are now going to move with the translocations. So let's begin. Translocation refers also to the transfer of soil constituents. This involves the movement of inorganic and organic materials laterally within a horizon or vertically, meaning up or down, from one horizon to another. The downward translocation of ions, clay, and mineral fragments such as silica tetrahedra that recombine to form clay is important to the formation of subsoil horizons. And over time, this process is one of the more visibly noticeable as alterations in color, texture, and structure become apparent. Downward translocation stops where the wetting front stops, as what you can see on the figure. This is the wetting front here. Maybe at the shallow depths in arid and semi-arid regimes, that is because of relatively lower rates of rainfall, and maybe mostly out of the profile when it comes to humid areas because of higher rates of rainfall. Now, upward translocation of salts is important to the formation of the saline and alkali or alkali soils of arid and semi-arid regions. The upward translocation stops at the soil surface where water evaporates. And then when the water stops moving, then evaporates, salts are left behind. Soil layers with calcium carbonate or other salt accumulations form this way. And if this cycle occurs several times, a calcareous hard pan can form. What is a hard pan? Hard pan is a hard, usually clay-rich layer of soil lying at or just below the ground surface, in which soil particles are cemented together by silica, iron oxide, calcium carbonate, or organic matter that has precipitated from water percolating through the soil. Hard pans do not soften when exposed to water. Water also can move fine clay particles, can dissolve salts, and dissolve organic substances through the soil through percolation and capillary action. And also, the soil organisms such as the earthworms incorporate organic litter into the A and B horizons of the soil. A horizon or the upper part of the soil profile and B horizon or the lower part, meaning from the topsoil to the subsoil. The mound-building organisms such as termites transport materials from deeper in the soil, meaning from B and sea horizon to the surface, meaning from the bottom to the top. The burrowing of rodents also transport materials through the soil. Chelation also helps in translocation. By the way, what is chelation? It is when metal ions, such as the iron and aluminum, combine with organic molecules released during the humus formation. The combination of the organic material or organic molecules and those metal ions, such as iron and aluminum, or organic metal chelate, is more soluble than the iron or aluminum mineral that is readily transported throughout the soil. So that's all for part 3. Please don't forget to like and subscribe for part 4 where we will discuss the other two soil forming processes such as the additions and losses. Thank you.